Hello everybody, chapter 2, lesson F. I'd like to get into some graphing today, so let's graph some rational functions. Also a little bonus again today for some oblique asymptotes, so not horizontal, not vertical, but slanted. We'll get into that at the very last slide. All right, let's get started. All right, so graphing rational functions, you guys, there are 6, I guess you could call them official steps. I don't think once you do 2 or 3 or 4 of these and you feel comfortable with it that you'll follow this pattern. But that's totally up to you. If you're a concrete type person, you got to have, steps 1 through 6 executed, and then cross off something on a to-do list and do a set of push-ups and then do this and that. Like, if that's your personality, by all means, take advantage of it. If not, get the general concept and then make sure and hit all of the essentials. So let's go ahead and look through the steps for graphing a rational function. First of all, you want to simplify f of x if possible. But prior to doing that, make sure that you note the domain restrictions before doing the simplifying. So the domain restrictions would end up being your critical values where you have a vertical asymptote or a hole. Okay, so step 2, find and plot the y-intercept. So find f of 0. Note that. Okay, I would plot them as well in the graph. Find the zeros of the numerator, if any, and plot those. Those are the x-intercepts. The zeros of the numerator are the x-intercepts. Step 4, we've kind of already noted in step 1, but find the zeros of the denominator, if any are present. This will identify the vertical asymptotes and the holes. You'll want to locate and identify the horizontal asymptotes by looking at the degree analysis of the numerator and denominator, and then plot multiple points between the x-intercepts and vertical asymptotes, as well as beyond them. That will give you an idea of the shape of the graph. So let's go ahead and do this for g of x below. Okay, so number 1, can't simplify, but I'm going to note the domain restrictions. So the domain of g of x is that x cannot equal 2. Since I don't see an x minus 2 in the numerator as well, that's going to be a vertical asymptote. So you can kind of note that for, I think it's, that would be step number 3. Step number 4. Okay, step number 2, it says find and plot the y-intercept. So if I plug in a 0, I'll get a negative 3/2. Okay, so I'm going to plot that here. I don't know what the graph looks like yet, so I'm not going to put the actual ordered pair up there quite yet. Okay, step number 3. It looks like the zeros of the numerator, well, 3 will never equal 0. Therefore, there are no x-intercepts. X-intercepts, none. Okay. Okay, let's move on to number 4. Number 4 is find the zeros of the denominator. We already did that. The 0 of the denominator shows us this vertical asymptote at x equals 2. So let's go ahead and put a vertical asymptote here at x equals 2. Okay, there's our vertical asymptote, x equals 2. Always do that with a dotted line. Okay, let's find the horizontal asymptote now for number 5. So if you look at g of x, the degree of the numerator, okay, so the degree of the numerator is 0, 0. Close that off, good. Degree of the denominator is 1. I'll abbreviate 1. That's a 1. So if the numerator's degree is less than the denominator, then we know we'll have a horizontal asymptote at y equals 0. Okay, I'm going to go ahead and sketch that. And label y equals 0. Perfect. Okay. Number 6, plot multiple points between and beyond the x-intercepts and the vertical asymptotes. So I only have one vertical asymptote. So I'm going to plot, let's say, 2 points to the left and 2 points to the right of our vertical asymptote at x equals 2. So I'm going to go out here. Let's go x equals 4 and give it a nice shape. Let's go out to x equals 7. That'll give us an idea of what the graph's going to do there. I've already got this point at 0, -3/2. So let's go maybe out to -4. Let's see what our sketch of our graph will look like there. Okay, actually I'm anticipating what this graph will look like, so I'm going to go here for x equals -4. Okay, so let me just real quick put some values here. Oops, I don't want that there. And you can kind of see what I'm doing. I'm shaping the graph here. Okay, so let's find the values for g of -4 and g of 4 and g of 7. And that'll allow us, you guys, to see the shape of this graph. Okay. Okay, so g of -4 would be -1/2. Okay, that would be a 3 over a -6, which is -1/2. G of 4 will be 3/2. Okay, and g of 7 will be, let's see, 3/5. Okay, so let's plot those. -1/2 for g of -4, and g of 4 is 3/2, and g of 7 is 3/5. Okay, so what I'm seeing here, and I know my end behavior, right? So if I have a horizontal asymptote at y equals 0, my end behavior on the right of g of x will equal 0. So my graph is going to head this direction and approach 0. The same will be true for the end behavior on the left. So as x approaches -infinity of g of x, we're going to have a 0 as well. So our graph will look kind of like this on the left side. If we were to test values really, really close to 2, let's go with like g of 2.1. Well, that would be 3 over 2.1 minus 2, which is 3 over 0.1. That's going to be a really large number, like 30. So g of 2.1 will be way up here. So we're going to be approaching this vertical asymptote headed way up, uncountably high. Okay, and g of 1.9 will equal 3 over 1.9 minus 2, which will be 3 over -0.1, which will be -30, right? So proportionally speaking, that's what our graph's going to look like, you guys. It's going to be that vertical asymptote. Looks like we're not going to be crossing the horizontal asymptote like I noted in the prior lesson, but that would be an accurate and sufficient graph of g of x. All right, let's get into another example on the next page. Okay, so I just wanted to note, forgot this, but in example 2, I wanted to note that in example 1, this is just a transformation on the parent function of 1 over x. So you'll notice here that g of x is a vertical stretch, right? It's been multiplied by 3 of a factor of 3, and it's been shifted right 2 units, right? So if I took the graph of 1 over x, which everybody should be very comfortable. Oh my gosh, that was great. This is not perfect, but it's a decent sketch. Right? If I took that, which has vertical asymptote at 0, that's x equals 0, and a horizontal asymptote at y equals 0, and I stretched it by a factor of 3, and I shifted it to the right 2 units, I would get g of x. So note that you can, once you get comfortable with these transformations on parent functions, you can utilize your parent function, stretch those outputs, and shift left or right. Okay, now we typically don't put more than 3 transformations on a function just because then it gets real messy and it's not worth it, and it's not very applicable to higher level math like calculus and others. So, but you can utilize your understanding of transformations in order to work and sketch a graph of a rational function very efficiently, more efficiently so than doing the 6 steps and noting all of that stuff. Okay, obviously here I didn't label everything. I didn't label 2 points on either side. I didn't do a real good job, but it was just a basic idea of showing you how that parent function applies to the previous function we graphed. Okay, so let's get on to a couple more examples. Okay, example 2 here. Let's go ahead, and if we can simplify, let's do it. Looks like number 1 is already done. We cannot simplify further. However, we can note that the domain of f of x will be x not equal to 0, and it looks like we've identified a vertical asymptote at x equals 0. So I'm going to go ahead and actually sketch that. Okay, there's my vertical asymptote. Number 2 on our 6 steps was to find and plot the y-intercept. Well, the y-intercept will not exist, right? Because if I plug in a 0, okay, if I plugged in a 0, I would get 2 times 0 minus 1 over 0, right? So that doesn't exist. Does not exist. And I should have known that with a vertical asymptote. We know the function can't cross that. Okay, not worried about a y-intercept. Let's look and find the zeros of the numerator. Okay, the zeros of the numerator will find for us the x-intercepts. So it looks like if I set 2x minus 1 equal to 0, then I would get x equal to 1/2. That is going to be an x-intercept. X-intercept will be 1/2, comma 0. Let's note that. Okay, I'll label that in just a moment. Number 4. Number 4 asks us to find the zeros of the denominator. This is going to help us find the vertical asymptotes and wholes, which we've already done. So the 0 of the denominator is at x equals 0. Okay, number 5. Number 5 asks us to find the horizontal asymptotes. So we look at the degree of numerator and denominator. Looks like the degrees are both 1. Therefore, we take their coefficients, which are 2 and 1. So we will have a horizontal asymptote at y equals 2. Let's label that. So I think proportionally speaking, this would be y equals 2. Okay, we've got a vertical asymptote at 0 and a horizontal asymptote at y equals 2. Now what we're going to do is we're going to plot at least 2 points on either side of the the vertical asymptote. All right, so let's do, we've already got f of 1/2 is equal to 0. Let's work with, I don't know, let's go out here. So this would be f of 2, 3, 4, 5. Okay, so that's 5. Let's do f of 5. Let's go f of negative 1/2 and f of negative 5. Keep it symmetrical here. Okay, so f of 5 would be 2 times 5 minus 1 over 5. So f of 5 would be equal to 9/5, which is just short of 2. So f of 5 is just short of 2. That makes sense. Okay, f of negative 1/2 will be 2 times negative 1/2 minus 1 over negative 1/2. All right, that will be equal to 2 times negative 1/2 is negative 1, minus 1 is negative 2, over a negative 1/2 will be a positive 4. Okay, so a positive 4 would be up here. point -1/2, positive 4. Again, let's note this. This is 1/2, 0. This point here is 5 9/5. Let's look at f of -5. That'll be 2 times -5 minus 1 over -5. So f of -5 will be equal to a positive 11/5, which is just over 2. Okay, so here at -5 would be this value, -5, and positive 11/5. That's 2.2. Okay, so the sketch of this graph, of course, with my end behavior, I know as I head, x heads to the right forever, it looks like the sketch of the graph will do something like this and approach the vertical asymptote from the right, headed to -infinity, and then the opposite the other direction. All right, there we go. We got a graph of 2x minus 1 over x. Let's go to another example. Okay, this example has a bit more complexities to it, but we're going to treat it exactly the same. First thing we're going to do, like we did on the last slide, is we are going to go ahead and find domain restrictions as well as simplify. So I'm going to factor numerator, denominator. Numerator will be x minus 3, x plus 3. Denominator will be x, what would that be, minus 3 and x plus 1. Okay, so I know the domain of f of x will be -infinity to -1 unioned with -1 to 3 unioned with 3 to infinity. Okay, so I know that there's going to be a vertical asymptote at -1. And there's going to be a hole at x equals 3. Okay, so let's note that. Vertical asymptote at x equals -1. And a hole at x equals 3. 1, 2, 3. So now I don't know where the output is for that yet. But I'm going to know in just a minute. So I'm going to simplify f of x. And I didn't leave myself a whole lot of room here. So I'm just going to scratch this part out here. So f of x, when reduced, will equal x plus 3 over x plus 1. So once it's been simplified, you can evaluate and find out where the hole is located. So I'm going to plug a 3 into that. So f of 3 would be equal to 6 over 4. 6 over 4, or 3/2. So I'm going to put a hole at the point 3, comma 3/2. All right, 3, comma 3/2. So over 3 and up 3/2. So I'm going to put a hole right there. That's 3, comma 3/2. Very good. Okay, let's move on to step 2. Step 2 is find the y-intercept if it exists. So f of 0, after simplifying, will be 3 over 1. So that will be right 1, 2, and 3. We got a y-intercept here at 0, 3. Okay. Step 3 is find the zeros of the numerator. Okay, so the zeros of the numerator are applied after we simplify the function. Okay, so I'm going to set x plus 3 equal to 0. That means x equals -3 will represent an x-intercept. So an x-intercept would be the point -3, comma 0. So let's go over to -2, -3, 0. Okay, so this would be the point -3, comma 0. Okay. Number 4 is find the zeros of the denominator. we already did that. And we found a vertical asymptote at x equals -1 and whole at the point 3, 3/2. Okay, number 5 is find horizontal asymptotes. Well, the degree of the numerator and denominator are the same. They're both 2. Therefore, their coefficients 1 and 1 will give us a horizontal asymptote at y equals 1. Number 6, we just need to plot a bunch of points, which we have already done. I'm going to plot one more point after I put this horizontal asymptote up. Okay, that's the horizontal asymptote at y equals 1. I can see the shape of the graph on the right side of the vertical. Oh, that was poor. On the right side of the vertical asymptote, it's going to look kind of like this. And of course, skipping the whole, there's a discontinuity there. I'm anticipating that I'll have on the left side, I'll have a little Southwest sauce there. And let's do this. Let's find the output for, oh boy, I don't care. Let's go -2. Yeah, let's do -2. So I've already got a bunch of points. I'm going to just find f of -2. And that would be, let's see, it'd be a 4 minus 9 over 4 minus, oops, that'll be plus 4 minus 3. So f of -2 will equal -5 over 5. So -1. That worked out nicely. That'll be, oh, and look at that. Oh my, that was nice. -2, -1. All right, that's a sketch of f of x. On the last slide, you guys, I'm going to go over the bonus information on slant asymptotes. So stay tuned if you're interested. Okay, guys, here's example 4. A slant asymptote exists when the degree of the numerator is exactly 1 more than the degree of the denominator. To find the equation of the slant asymptote, we'll end up using long division. So first, let's go through some of these steps. Find vertical asymptote, find some points. I'm going to find the slant asymptote kind of in the middle of all of that. So 1, the domain, I can't simplify, so I'm not going to have to do much with that. The domain of f of x will be x not equal to -1, and what that'll be is a vertical asymptote. -1. Okay, number 2, find and plot the y-intercept. Well, if y equals 0, excuse me, if x equals 0, I'm going to get 0. So I've got a y-intercept. F of 0 does equal 0. There's our y-intercept. Number 3, find the zeros of the numerator, if possible. These are the x-intercepts. So what I would have here is if I set x squared minus x equal to 0, I could factor x minus 1 times x equal to 0. Therefore, I'd have x-intercepts at 0, 0 and at 1, 0. Okay, number 4. Find the zeros of the denominator. I already did it. I got a vertical asymptote at x equals, vertical asymptote at, not equal to, x equal to -1. Okay, so I'm going to plot that. Okay, I got a y-intercept at 0, 0. I got x-intercept at 1, 0. Okay, that's 1, 0. Okay, let's take a look at our slant asymptote. Since there is no vertical asymptote, or excuse me, horizontal asymptote, none, we're going to explore what's called a slant asymptote. So we can find the equation of the slant asymptote by doing some long division. So I'm going to take x plus 1, and I'm going to divide it into x squared minus x plus 0. So x times x gives me x squared, and x times 1 gives me x. I'm going to subtract. That gives me negative 2x. I'll drop down to 0 just for the heck of it. So it looks like I want negative 2. So that would be negative 2x, and that would be minus 2. Okay, we're getting close here, guys. I'm going to have a remainder, it looks like, of 2. So x squared minus x divided by x plus 1 is equal to x minus 2 plus 2 over x plus 1. Now, the equation of the slant asymptote comes in this linear form. So x minus 2, I'm going to graph x minus 2. It'll look like this. Here's a y-intercept. The slant asymptote will follow that equation. All right, so this is really weird, but let's find some points for part 6. All right, let's find, let's go. We've got these 2 points at 0, 0, and 1, 0. Let's see what happens in between them. Let's plug a 1/2 in there. So we'll find f of 1/2. And then let's find f of negative 2 and f of negative 4. F of negative 2, f of negative 4. Okay, so f of 1/2 will be 1/4 minus 1/2 over, that'll be 3/2. So that would be negative 1/4 over 3/2. Let me do some side work here. Negative 1/4 over 3/2 would be equal to negative 1/4 times 2/3, which would be equal to, that would be a negative 1/6. Okay, so it looks like we get something in here. All right. Here's what I'm anticipating this graph to look like, and you could confirm that graph is going to look like that. That's pretty cool. It's pretty darn cool. Let's look at negative 4 and negative 2. And actually, I'm going to scratch negative 4, and I'm going to go with negative 3. So I'm going to go with negative 3 here. So f of negative 2 is going to be 4 minus a negative 2 over a negative 1. So that'll be negative 6. Okay, so f of negative 2 is negative 6, which will be down here. Negative 2, negative 6. Oh boy, so negative 3 is going to be probably much smaller than that. That'll be 9 minus a negative 3 over, what is that? Negative 2? Yeah, okay. That'll be 12 over negative 2, which also comes out to be negative 6. So I'm guessing what the function does over here is something like this. And you could test in between the two at negative 2.5. But that would be a graph of f of x finding the slant asymptote. And of course, I didn't label the slant asymptote. I'm a bad teacher. This would be the function of y equals x minus 2. That's our slant asymptote. Of course, that was right here. Okay, guys, that's graphing rational functions. I hope it went well. Make sure and overemphasize labeling. I didn't do a great job of it. I should probably put all of my points up here so that I'm being a good model of what we should be doing. This would be, what was that, 1/2, negative 1/6. And I think I labeled everything else, so, oh, I forgot, I gotta label this f of x. Otherwise, who would know what you're even talking about? Okay guys, have a great day. We'll see you in the next video.